In lesson 4, we're going to start proving identities. So proving an identity is basically a way to verify that two trig expressions are identical. So we will be using a variety of identities. They are actually on your formula sheet. So this will be one of the times that you'll always want to have your formula sheet out with you. Some of them are on the formula sheet and some of them are not, because some of them we already know. So for example, we should already know our tangent and cotangent identities just from what we know about the unit circle. Tan theta equals sine theta over cos theta, and cotangent theta equals cos theta over sine theta. We also already know all of our reciprocal identities because we know cosecant's the reciprocal of sine, secant's the reciprocal of cos, and cotangent's the reciprocal of tan. So notice that we can change these either way. So what I mean is, just like we can say cosecant is 1 over sine, we could also say sine is 1 over cosecant. We also have some Pythagorean identities that we're going to work with. So for example, the main one is the fact that sine theta plus cos squared theta equals 1. And this comes from our unit circle formula, where x squared plus y squared equals 1. So if we think about that fact from the unit circle and the fact that x and y are related to sine and cos, this is where sine squared theta plus cos squared theta equals 1 comes from. The other identities under the Pythagorean identities are also really important. We're going to talk a little bit more about those as we start to kind of approach questions with them. So just another note, though, that all the tangent, cotangent, and reciprocal identities can be squared and they can still be true. So for example, we could say that tan squared theta is the same as sine squared theta and cos squared theta. However, this does not apply for the Pythagorean identities. So for example, just because sine squared plus cos squared equals 1, that does not mean that sine theta plus cos theta equals 1. This is not true. So please make sure that while you can square tangent, cotangent, and reciprocal identities, and they are still true, this does not apply to the Pythagorean identities. So verifying and proving identities is really like a puzzle. Sometimes you get started and you realize you're maybe not on the right track and you need to go back and you need to restart. So don't be discouraged if you find that you're doing a lot of erasing. It just comes really a lot with practice because you need to really think about where your end game is. The other thing about identities is there's always more than one way to do it. There's lots of different strategies. So just because you're maybe taking a different approach than somebody else doesn't mean that you're going to get to a different answer. Basically, your goal is to always show me that the left-hand side equals the right-hand side. How can you make both of those the same? So there are some strategies to verify identities. You always want to try to work with the more complicated side first. So what has more trig functions? What has more that you can see yourself changing or working with? As needed, write everything in terms of sine theta, cos theta, and tan theta. So sometimes when you have those reciprocal identities, cosecant, secant, cotangent, it's just easier to try to change them so that they're all your primary trig functions. Replace the more complicated expressions with similar ones. Try to write all the terms over the same denominator. That's another strategy. So we're just going to get started, and as we work through them, hopefully you'll kind of develop some of your own strategies that work for you. So when we prove our identities, we always work in this T-chart table, and you'll be provided a T-chart table on your assessment to work with your identities. So we just really want to make sure that we understand that the left-hand side and the right-hand side are being worked with separately. So we're not going to be using equal signs within our T-chart. That's why it's there to help us stay organized. So you can either work with both sides or you can work with one and try to make it equal the other. So I'm going to start with the 1 plus cotangent squared theta, and that's just my left-hand side. So you don't need to work with both sides. I'm going to look for the one that seems a bit more complicated, which is the 1 plus cotangent squared theta, and I'm going to just start with that. All I'm going to do is I'm going to work down, and I'm just going to start changing things, keeping in mind my end game is to somehow get to this cosecant squared theta. If I can work the entire left-hand side and end up at cosecant squared theta, then I've proven the identity. I don't have to do anything on the right-hand side if I don't want to. With that being said, I can work exclusively on the right-hand side, or I can actually work on both sides, and I'll show you those different strategies as we go. So the first thing I'm going to do here is I'm actually going to try to change the cotangent to coses and sines. So this will be 1 plus, cotangent is cos over sine, so cotangent squared then is cos squared theta over sine squared theta. So all I've done is rewrite this. Every single time I do a step, I'm not changing the meaning of the left-hand side. I'm just writing it in a different way. A few things to be mindful of: that you're not losing any thetas along the way, that your squareds are written in the right spot. You don't want the squared after the theta. You want it between the cos and the theta, or the sine and the theta. So once I look at this, I recognize that if I want to combine this further, I'm actually working with adding fractions, and in order to do that, I need a common denominator. So all I'm going to do is change the 1 to be over sine squared. So my next step is going to change 1 over 1 to sine squared over sine squared. Okay, don't forget the thetas even though I'm not saying them. Okay, the next part stays the same. So again, all I've done is rewrite the left-hand side, has the same meaning, just looks different. Now that I have a common denominator, since everything is over sine squared theta, I'm just going to simplify this in my next step. My bottom is sine squared theta, and all I'm going to do is take my numerator and just combine it over the 1 denominator. Okay? Now, what you should notice here is that we actually have our Pythagorean identity. Remember that if you look back up at the top, sine squared plus cos squared equals 1. So as soon as I see a sine squared plus cos squared anywhere in my identity, I can change this whole thing here to 1. So instead of sine squared plus cos squared in my numerator, I'm going to have 1 in my numerator. My denominator stays the same. Now, if I want, I can keep going here, because I should recognize that 1 over sine is cosecant, so 1 over sine squared is cosecant squared. So you can keep going on the left, or your other option is you could work with both sides. So maybe you decide at any point to stop on the left-hand side, and then you move to the right-hand side. Well, what do I know about cosecant? Well, I know cosecant's 1 over sine, so cosecant squared is 1 over sine squared. As soon as I have made the bottom of my left-hand side and the bottom of my right-hand side the same, then I have proven the identity. So I could either have done it by continuing with the left-hand side to make it equal cosecant, or again, working with both sides, changing them both to the same thing. As soon as I've written this, I need to write a final statement. These 3 dots mean therefore, the left-hand side equals the right-hand side. And that is my proof. Again, there are multiple ways to do it. Make sure that if a question is asking you to prove an identity, that it can be proven. Don't write that it's not true, it can't be proven. If you're being asked to prove it and you're being told that it's a true statement, it is in fact a true statement. Okay? All right, let's try another one. Example 2. So again, you kind of need to decide what side do you want to start with. I always like to pick the side that I feel looks a little bit more complicated, and that's going to be the left side. So right away when I look at the left side, I think about sine squared theta, and I recognize that I have an identity for sine squared theta. So let's just go back for a second here. Okay. If sine squared theta plus cos squared theta equals 1, that means that I can rearrange this identity to get multiple identities. So for example, what happens if I want to isolate sine squared here? Well, that means that sine squared equals 1 minus cos squared theta. So with that being said, if I look back at the other identity that I was just working on where I had a sine squared, that means I can change the sine squared to 1 minus cos squared theta. So this is again where having your formula sheet beside you is going to be really useful. So this now becomes 2 takeaway in a bracket 1 minus cos squared theta, and the bottom stays as cos theta. Okay. The bracket's important because it's subtraction. In my next step, I'm going to get rid of the bracket by distributing the negative. So I have 2 takeaway 1 plus cos squared theta all over cos theta. Notice I'm not using any equal signs within my charts. Now I can just simplify the top because I can combine the 2 minus 1, and this is going to give me 1 plus cos squared theta all over cos theta. So you can keep working with this side if you want, or you can say, okay, well, I feel like I've gotten this all in terms of cos. Maybe I can go to the right-hand side, and if I work with that, maybe I can get that all in terms of cos. So let's go to the right-hand side. Okay. I can change secant theta to 1 over cos theta, and I can keep that cos theta the same. Keep in mind that cos theta is technically over 1. Okay, and you can kind of look back and forth between your left side and your right side. Your end game is that you're trying to make them the same. So I can see that on the left-hand side, everything is over cos theta. So what can I do to the right-hand side to make that the same? Well, let's find a common denominator here. So if I need to find a common denominator, I need to multiply this second fraction by cos theta. So I'm going to end up with 1 over cos theta plus, this now becomes cos squared theta over cos theta. And you can see now that you have a common denominator, you can write the whole thing over cos theta, and you end up with 1 over cos squared theta. 1 plus cos squared theta over cos theta, sorry. And you can now see that the left-hand side equals the right-hand side. Okay? All right. So if I wanted to strictly work with the left-hand side, just a note, and I'm going to do this in another color just because you don't want to get confused and do too much work. If I chose to just keep going with the left-hand side, I just want to make sure that you know that if you have a polynomial over a monomial, like we do here, I can rewrite this as 1 over cos theta, right? I can separate it the same way that I would put it together if they were the same. I would then recognize that this is 1 over cos theta plus, here the cos squared theta over cos theta is just cos theta, which you can then see if you go one more step, the 1 over cos theta becomes a secant theta, and then you have the right-hand side without having to actually work on the right-hand side. So that's just another option. You don't have to do it in more than one method. All right, let's look at example 3. You'll notice that with example 3, there's 2 t-charts. That's because we're just going to do it in 2 separate ways. I just want you to see the different strategies that exist. So I'm going to do it in one t-chart. I'm going to work with both sides, kind of like I did for example 2. And in the other t-chart, I'm just going to work with one of the sides. Okay? So I'm going to start with working with both sides. And again, I'm just going to notice that this sine squared theta, just like above, I can change it to 1 minus cos squared theta. So let's go ahead and do that. So this becomes 2 times 1 minus cos squared theta minus 1. And I'm going to kind of just keep working with this side until I feel like I have it simplified, and then I'll jump to the right-hand side. I'm going to distribute the 2. So this becomes 2 take away 2 cos squared theta minus that 1. I'm going to combine my like terms. So 2 take away 1 is 1. Notice that other 2 is attached to the cos squared theta. So I'm going to stop there on the left side because I feel like I have a pretty good handle of this. I basically have gotten everything in terms of cos. So now when I look at my right-hand side, I say to myself, well, if I do the same substitution, then my right-hand side will also only have coses. So I'm going to take my right-hand side, I'm going to change that sine squared to 1 minus cos squared, and then I still have that second cos squared theta being subtracted. Now I'm going to put together my like terms. Oops. Well, negative cos squared minus cos squared is just negative 2 cos squareds. And then you can see right there, you can stop. You're done. You've just done 2 or 3 steps on each side. You've made both sides equal the same thing, so you can say the left-hand side equals the right-hand side. Okay, so that's one approach. Let's take an approach where we just work with one side completely until we make it the other side. So I'm going to actually work with the right-hand side. Again, you can do this in multiple ways. So a challenge for you would be to try this exact same proof on your own and see if you can find a third way to do it. So when I look at what I'm starting with on the right-hand side, and I look at the left-hand side to start only has sines. So when I look at this, I want to try to change everything to sine squared. So I'm going to go back for a second to this Pythagorean identity here, because we can rewrite this in another way. If sine squared plus cos squared equals 1, we can get sine squared by itself by moving over the cos squared to 1 minus cos squared. But what if we want to take this and we want to get cos squared by itself? Well, then we're keeping the 1 where it is, and we're subtracting the sine squared. So this identity works for both sine squared and cos squared, where we can just plug in 1 minus the opposite. Okay? So with that being said, let's go back here. And since I know that the left-hand side only has signs, let's try to make the right-hand side only have signs, which means I need to change the cos squared somehow. I now know cos squared could be 1 minus sine squared. So let's substitute that in. Sine squared theta minus bracket 1 minus sine squared theta. So you should already start to see that we're getting closer to what the left-hand side started as. We're going to get rid of the bracket by distributing the negative. Okay. We're going to combine our like terms. So we have a sine squared plus a sine squared. So then we have 2 sine squared thetas, and we have that minus 1. So you should notice at this point now we're done, because if you look at what the the left-hand side started as, we're already there. So we've just worked with one side. It took us about 3 steps, but we got there. So we can then say therefore the left-hand side equals the right-hand side. Okay, so hopefully you're starting to get a bit of a feel for what you're looking for. We're going to keep going. We're going to just start to incorporate some more of our identities. Okay, so we're going to go back to these Pythagorean identities, and we're going to talk a little bit more about the rearranging. So we've already talked quite a bit about the fact that if sine squared theta plus cos squared theta is 1, then we can rewrite it to get sine squared by itself, or we can rewrite it to get cos squared by itself. Another thing, though, is that we can also take our other Pythagorean identities. So we've got this tan squared theta, and this one with the cotangent squared theta. Okay, so tan squared theta plus 1 equals secant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. Okay, we can take these and we can also rearrange them in different ways. So each Pythagorean identity actually has 3 versions, one where everything is kind of isolated. So here we can also get tan squared theta by itself, simply by taking that 1 and moving it over. Okay, so that's another identity. In the second one, the one with the cotangent, we could get cotangent by itself by keeping the cosecant where it is and moving the 1 over by subtraction. So these are other identities that we could work with. Excuse me. You might notice that the secant squared theta minus 1, the cosecant squared theta minus 1, as well as some of our identities above, those can also all be factored using difference of squares. So another option would be to say that tan squared theta equals, if I take the secant squared theta minus 1 and I factor it using difference of squares, that's secant theta plus 1 and secant theta minus 1. So that is another version of that identity. If I take this cotangent squared theta, and I look at the right side, the cosecant squared theta minus 1, that is also difference of squares. Cosecant theta plus 1 times cosecant theta minus 1. Okay. If you look above, you can see that the same thing applied for if you just have sine squared or cos squared. So that just comes from the fact that you're factoring difference of squares. So these are just all a whole bunch of extra identities. You have the base ones on your formula sheet. You just have to be able to be flexible with manipulating them if you see you need to in a question. All right, so we're going to just do a whole bunch more identities together, and then you're just going to practice them. It really just does come from practice. So let's look at example 1. So in this case, I'm going to look at the left-hand side, and I'm going to start there. Okay, so cos theta over 1 minus sine theta. Now there's a reason I've written it all into the side here, because when I look at this, I don't have anything I can replace this with. I need a cos squared or a sine squared to be able to start using my Pythagorean identities. But what I should notice is if I look at the bottom here, I have part of a difference of squares. So if I multiply this by the 1 plus sine theta, then I know that that's going to introduce a squared into my denominator. Okay, we call this multiplying by the conjugate, which you might remember from grade 11. So this is another strategy with proving identities, is you can always multiply by the conjugate if you need to introduce a squared into the identity. However, whatever you do on the bottom, you need to do on the top. Okay. All right, so on the top now, I'm just going to leave it. I'm not going to distribute it in. I have cos theta times 1 plus sine theta. And on the bottom, this is difference of squares. So when I multiply this, when I FOIL it, the inside and the outside will cancel. So this just ends up being 1 minus sine squared theta. Again, this is from grade 11 when you multiplied conjugates, for example, to rationalize your denominator. If you're not sure how I got to that, take the 1 minus sine times the 1 plus sine, go off on a scrap piece of paper, FOIL the whole thing out, and combine your like terms. Okay? So now as soon as I've introduced that sine squared theta, I can see that on the bottom, 1 minus sine squared theta is an identity. It equals cos squared. So cos theta is 1 plus sine theta on the top. That doesn't change. And on the bottom, I now have just a cos squared theta. If you're wondering where that came from, look up here and look at all of my different versions of my Pythagorean identities. So you might need to grab a piece of paper and you might need to write all these versions down for yourself. All right, so there's another reason why I didn't get rid of the brackets on the top, because now what you should be able to see is that I can do some canceling. The cos theta on the top is going to cancel with one of the thetas on the bottom. So now I'm left with 1 plus sine theta over cos theta. Okay. Another way I can write this, remember when you just have a monomial on the bottom, you can split up the top. So 1 over cos theta plus the sine theta over the cos theta, right? All I'm doing here is writing it as two separate fractions. 1 over cos theta is a reciprocal function. It can be rewritten as secant theta plus sine theta over cosine theta, that's just tangent theta. What you should notice at this point is that our very last line on the left-hand side already equals what we start with on the right side. So we can then say we have proven this identity, the left-hand side equals the right-hand side. Again, like I mentioned, this is just really something that's going to come with practice. There's more than one way to do it as well. So you might have chosen to start with the right-hand side and worked with that. Maybe introduce some of your secant and tangent Pythagorean identities, and that's fine as well. All right, let's try example 2. All right. So for this one, I'm going to actually end up working on both sides. Sometimes you don't know where you're actually going to end up or what your strategy you're going to use till you get started. Sometimes you really just have to work your way, get started. And sometimes, like I said, you start and you just got to go back and you got to start erasing. Okay? All right, so let's start with the left-hand side. And again, this looks very familiar to the last one where I don't have a squared on this side. So the only way I'll be able to introduce a square is by multiplying by the conjugate. So I'm going to multiply the top and bottom by 1 minus cos of x. So the top is just going to be 1 minus cos of x. The bottom, if you simplify it, is going to end up being 1 minus cos squared x. Okay. All right, so once I have 1 minus cos squared x on the bottom, that can change to sine squared x. Notice that the 1 minus cos on the top is not sine. Remember, we talked about how that's not a true identity. So the only thing I can change here is the bottom. I can also split these up now at this point. Okay. So now I'm going to kind of start looking ahead at the right-hand side. Am I any closer to where I want to be? Well, that 1 over sine squared x, that's looking pretty good because I can already see that that's cosecant squared x. The cos over sine x, I can see there's a sine, there's no cotangent, so I could keep working with that if I wanted to. Or I could maybe move to the right-hand side, see if I can rework the right-hand side to get to the same point I did on the left-hand side. So I'm going to work with the right-hand side. The first thing I'm going to do when I rewrite it is I'm going to change everything to sine and cos because I know that that's where the left-hand side ended. So the cosecant squared will become my 1 over sine squared x, which is great because that matches the left-hand side, minus. I'm going to rewrite the cotangent x. So remember, cotangent x is cos x over sine x. So that's going to be my numerator. So cos x over sine x, but that's still all over the original sine x. Okay? So I'm going to go do a little bit of the work off on the side here now. I just want to rewrite what this actually means. Cos x over sine x divided by that sine x, which technically is over 1. So again, if you want to do rough work, you can always do rough work on the side of your paper. Just make sure it's very clear that it's not part of your answer. It's just your rough work, or do it on a separate paper. So how do I divide fractions? Well, you're going to keep the first fraction the same. You're going to change the division to multiplication, and you're going to take the reciprocal. Once I do this, I can now see that I'm just multiplying top times top and bottom times bottom. So let's go and fill that in now to our chart. So the 1 over sine squared x is not changing, minus this whole thing right here, okay, I just worked off on the side with, becomes cos x over sine squared x. And you can do some of that work as well within your identity if you want, but you can see how it could get a little confusing. Once I've gotten to that point, I should recognize that I'm done. The left-hand side and the right-hand side are now identical. All right, example 3. So I'm definitely going to want to work with the left-hand side here because I can tell that it's much more complicated. The right-hand side does not have much going on. So I'm going to start with the left side. And as soon as I notice that I'm working over a monomial, I'm just going to split up this division. 1 over tan squared theta plus tan squared theta over tan squared theta. Okay. Well, 1 over tan squared theta is just the same as cotangent squared theta plus tan squared divided by tan squared is 1. If you look on your identity sheet, you can see that we actually have an identity that says cotangent squared theta plus 1 is cosecant squared theta. Notice too, just one note, that in example 2 they're using x's, example 3 they're using thetas. Please make sure that you're staying consistent. You're just always wanting to keep the same variable that the question uses. So this one was actually very straightforward. The left-hand side equals the right-hand side. All right, let's look at example 4. Okay, so again, sometimes you just really don't know if you're going to end up working with both sides or one. I'm going to always start with the side that looks a little bit more complicated. I'm going to start with the left-hand side here. So I have sine squared theta over secant theta plus 1. So I always kind of want to think like I could change that sine squared theta to 1 minus cos squared theta. That would be an option. The other thing I could do is realize that sometimes it's nice to have just one term in the denominator. So if I start maybe multiplying by the conjugate, I'll get that one term on the bottom. So I also definitely encourage you to take any of these examples that we've done and try them in a different way. So if you were going to say to yourself right now, no, I would prefer to change the sine squared theta, then definitely by all means, I recommend trying that. Sometimes we try something and it just makes it more confusing rather than less, and we have to erase, and that's okay. So the top I'm going to leave as it is. I'm going to FOIL the bottom, which is going to give me a secant squared theta minus a 1. This is an identity. Secant squared theta minus 1 is just tan squared theta. So I'm going to keep the top the same. And I'm going to change the bottom to tan squared theta. Okay. All right. Now, it doesn't really look like I have much yet to help me. But what I should recognize is that I'm trying to get to the right-hand side, which doesn't have a denominator. So my goal is to cancel out that tan squared theta denominator somehow. So what I'm going to try to do here is rewrite that tan squared using sines and coses. So in my next step, I'm keeping the top the same and I'm just working with the bottom. So sine squared theta times secant theta minus 1 stays the same. Tan squared is sine squared theta over cos squared theta. Okay. So again, if you think about what this means, it means you're going to end up flipping and multiplying. So the cos squared theta is going to multiply up on the top, and the sine squared theta is going to be your division. So again, if you do need to go off onto the side to do a little bit of rough work, okay, this is going to end up being sine squared theta times secant theta minus 1 times, because we have to flip it, cos squared over sine squared. So you can see what's happening here is the sine squareds are going to cancel. Okay, so on the top, I'm going to have a cos squared theta times a secant theta minus 1. Okay. All right, so we can keep working with the left-hand side. We're starting to run out of a little bit of room, okay? But I'm just gonna kind of keep going with it, pretending that I have more room. Maybe I'm gonna work up here. So now I've got the cos squared theta, and I'm gonna change the secant to 1 over cos theta minus 1. So this is still a continuation of the left-hand side. Now I'm gonna multiply because I know the right-hand side does not have any fractions or any brackets, so I end up with cos squared over cos for the first term minus cos squared theta. The first term can be simplified. Cos squared over cos is just cos theta minus cos squared theta. So again, this is my strategy. You might have started working with the right-hand side at some point and tried to make them equal. There's lots of different ways that you can work with this. Okay. All right, example 5. Last one that we're going to try together, and then like I said, this is really all just about practicing. Okay, how much can you practice this? How many different types of identities can you try using all the different strategies? Okay, so example 5, we've got a lot going on the left-hand side. So the first thing I'm going to do is maybe change everything to sine and cos on the left-hand side. So the numerator is already sine and cos. I'm going to change the bottom to 1 over cos theta plus 1 over sine theta. Now, because I'm adding fractions, I'm going to need to find a common denominator. So my common denominator on the bottom is just going to be cosine. So they're going to both need a cos and a sine. So the first one is missing the sine theta, so I'll multiply that top and bottom. The second one, I'll multiply the top and bottom by cos theta. So let's just rewrite this now. The top is going to stay the same. That's still sine theta plus cos theta. All over. Okay, so the new bottom is now going to be the same, so I don't have to have that step where I write it all separately. I can just combine it, and you can either write sine theta cos theta, or again, cos theta sine theta is also fine. The numerator now here is sine theta plus cos theta. So all I've done is rewrite this part all down here. Okay. Now I'm going to flip and multiply. So the numerator stays the same, and I'm going to multiply that by the denominator flipped, right? So this has to flip in my next step. Think about that long division. Again, if you want to go off on the side and do the full work, you can. But when you divide fractions, your first fraction stays the same, you change to multiplication, and you flip your bottom fraction. We should now be able to see that we have some crossing out we could do. Sine theta plus cos theta crosses out. So we are now left with sine theta cos theta. We could keep going here at this point if we want, or maybe we want to work with the right-hand side. Let's try that because we didn't do that for the last one. So here I'm going to change the secant. So I'm going to keep the sine theta the same. I'm going to change secant to 1 over cos. And why am I doing that? Because I see that on the left-hand side, everything is in terms of sine and cos. So I'm just really thinking about my strategy to get these the same. Then I am going to flip and multiply, which you can see when you multiply this, you have the left-hand side equaling the right-hand side. Okay. So the trick here is really to just make sure that you understand how to work with all of your algebraic expressions. So one thing that I want to note at the bottom is just a common error that I see happening. So for example, if you have something like this, 1 plus cos theta over cos theta, very often I see people canceling these cos thetas out. If it is a binomial, the 1 plus cos theta, it is one thing, it is stuck together. You can only cancel 1 plus cos theta with another 1 plus cos theta. You cannot just cancel part of them. Okay, so this is not allowed. Okay, this is not acceptable canceling. So don't do this. 1 plus cos theta over cos theta does not just become 1. So that's just a very common strategy that I see people trying to do to simplify things, and it just does not work that way. You have to remember that if you have a plus sign, you need to think of it as different than having a subtraction or a multiplication sign, which is when you can start canceling things out. All right, so again, that is just a whole bunch of examples with identities. These are just something that you just practice. They become easier over time. Some of them are just much trickier, as you can see. Some have more steps, some have less steps. It's really just about finding a strategy you're comfortable with working with them.